right, folks, today we are going to talk about momentum in the rotational motion, or otherwise known as angular momentum. So, the final analog to our translational motion when we think about rotational motion is angular momentum. This is a final variable that we have yet to discuss in the rotational capacity that we did discuss back when we were thinking about translational motion exclusively. And if we think about our linear momentum or translational momentum, we have P that stands in for linear momentum equals mass times velocity. And so obviously, P, we're going to come up with a new variable for because now this stands for angular momentum when we think about rotation. And the variable we use is a capital L. So capital L is angular momentum. And as we've already seen, our analog for mass or inertia from translational motion is now rotational inertia or moment of inertia, which we represent by a capital I. And our analog for translational velocity is angular velocity, which we represent by omega. So our angular momentum equation is capital L for angular momentum equals I for moment of inertia times angular velocity or omega. And if we think about the units here, linear momentum was expressed in kilograms meters per second squared, right? Because our mass, of course, is in kilograms and our velocities in meters per second. So our momentum in linear motion was kilogram meters per seconds. Right now, if we think about angular momentum, we've got our moment of inertia is expressed in kilograms meters squared rather than just kilograms. And our angular velocity is in radians, which isn't really a unit per second, right? So that's not really a unit. And so when we multiply those two together, we end up with kilograms meters squared per second, which is our units for angular momentum. All right, so let's try a practice problem here. So now that we know what angular momentum is, let's think about the Earth. And the Earth revolves around the sun. But sorry, we're not thinking about that. We're thinking about it as it rotates on its axis, right? So if we draw an axis from the North Pole to the South Pole, which may or may not be what this picture actually looks like, it is rotating in some capacity with an angular momentum of omega, and it's going to have some moment, a moment of inertia about it, right? So if we think about our angular momentum, it's going to equal our moment of inertia times our angular velocity. And so we need to come up with our our moment of inertia for the Earth, which the Earth is a solid sphere. So it's roughly an even mass distribution. It's not entirely correct, but we can treat it as if it has an even mass distribution and that it has a moment of inertia just like a solid sphere, which if we look that up, we know that a solid sphere has a moment of inertia of 2/5 times mr squared. Right. And we know that our mass of the Earth is 5.979 times 10 to the 24th kilograms. And its radius is 6.376 times 10 to the 6 meters. And that is squared. So we should come up with a moment of inertia for the Earth, a value for that, which is 9.72 times 10 to the 37th. And again, if we look at our units there, we've got kilograms times meters squared. So this would be kilogram meters squared, which is our moment of inertia units. So then we want to think about our angular velocity, right? And our angular velocity for the Earth equals the amount of radians it goes through over a period of time, which will just be 2 pi, right? We can think about how much time it takes for it to revolve make one full rotation, right? So if it makes 2 pi's worth or 360 degrees worth of rotation, that occurs over the span of 1 day. And if we take and we set that up into seconds. So 1 day for every 24 hours, for every 1 hour, we have 3,600 seconds. So we can convert into radians per second, which would be, If we multiply through here, 2 pi over 24 hours over 3,600 seconds, we get 7.27 times 10 to the negative fifth. And that's radians per second. Because we canceled out our days, canceled out our hours, and we're left with just seconds and radians on top, though again, radians isn't really a unit. So we can then plug all this back into our angular momentum equation. If we take our moment of inertia, so this is the inertia of the Earth as it revolves around its central axis, right? So that is 9.72 times 10 to the 37th kilogram meter squared. And we can multiply that times our angular velocity, which is 7.27 times 10 to the negative fifth radians per second. And we end up with some number. It's a really, really big number. It is 7.07 times 10 to the 33rd power. And again, we got kilograms meters squared and seconds at the bottom. So this is in kilogram meters squared per seconds. That should be the angular momentum of the Earth as it rotates about its axis. Okay, so when we were discussing linear momentum, we also thought about impulse, right? Which was just our change in momentum over time, and we could relate that to the net force acting on the object as it undergoes that change in momentum, times the amount of time that net force acts on that object, right? So obviously, we can come up with an analog for this for angular impulse, and obviously, our change in momentum. Linear momentum, the analog would be our change in angular momentum, right? Delta L. And that's going to equal, rather than net force, we're thinking about the net torque acting on an object and still multiplied times time. So the net torque times time should give us our change in angular momentum or our angular impulse for an object. And we can rewrite this equation if we wanted to solve for our net torque. So our net torque should equal our angular impulse divided by time. Okay, and we can put that idea of angular impulse into practice with a problem like this, which we are going to practice problems like this in class. But if you wanted to take a run at this one right now, you could pause this and you can work this problem. The answers are on the slide. All right, so just like with linear momentum, our momentum is going to be conserved over the course of an event. So just like with a linear system, angular momentum will be conserved over time as long as our system is closed. However, unlike with linear momentum, we're often going to encounter a conservation of angular momentum within a single object rather than any collision between two objects. So for instance, we can take a look at an ice skater, and an ice skater is going to change their rotational velocity by bringing their limbs into or out of their center of rotation. So let's take a look at that. All right, so we've got our ice skater who's going to come into a spin, and as her limbs are outstretched, she's spinning at some rotational velocity, but as she brings them in towards her center of rotation, her angular velocity increases significantly. Then she comes out of her spin. So let's think about what this means in terms of conservation of angular momentum. So there is no external net torque for the ice skater, right? So her angular momentum should remain constant. And if we think about our net torque, if it equals zero, then given that we have to have some net torque acting over time to change our angular momentum, then our change in angular momentum or our angular impulse should also be zero when the net torque is zero. Right? So if there's no change in angular momentum, then an increase or decrease in moment of inertia will result in the opposite for angular velocity. Because if our initial angular momentum, or just L, equals our final angular momentum, right, our L naught, then we know that our moment of inertia, our initial moment of inertia times our initial angular velocity has to equal our final moment of inertia times our final angular velocity, right? So over here, we've got some L, right, which is going to equal our moment of inertia times her angular velocity. But as she brings her arms in, her moment of inertia is going to decrease, right? Because now her mass is distributed more closely to the center. And that means that if these two have to equal one another, then if her moment of inertia prime, her final moment of inertia decreases, then her angular velocity at the end has to increase. And we saw from the video that it increases pretty significantly just by drawing those limbs in. And then we're going to work some problems like this in class, but you can take and you can do a problem like this where we can figure out what her angular momentum, or sorry, her angular velocity will be once she changes her moment of inertia by bringing her arms in. And we can also figure out what her kinetic energy is during those 2 points in time, before bringing her arms in and after. And finally, we can think about what changed in her kinetic energy. And again, since there's no net external force, basically she has to be changing her energy from within, right? And essentially, this occurs because whenever you do an athletic movement or a mechanical motion, right, you're converting chemical energy inside of your body from ATP to ADP, and that conversion of chemical energy will result in a change in motion, a change in your motion, a change in mechanical energy for your body. So we will discuss more questions like this in class as we continue to talk about angular momentum. Thank you for watching.